So the second part of the fundamental theorem of calculus says if I want to integrate some function from a to b, then there is some other function, capital F, which is a function that represents the area under f of x, little f of x. So that's what we're saying capital F is. Capital F is a function that represents the area underneath little f of x. Okay. Effectively, we call that the antiderivative or the integral of little f. So capital F is a function that you get when you integrate some other function, little f of x. Is everybody okay with that?
Yeah.
Okay. So for example, you should be able to think about this in terms of functions you already know. If I said the function f of x equals 1, what would capital F of x be? Or what's one function that it could be? It would tell us that the derivative of capital F of x needs to equal 1. So what function has a derivative that's equal to 1?
X.
X, right? It could be x plus 7 also, right? Or it could be x plus 1,000, or it could be x minus 10. But f of x equals 1 gives us capital F of x equals x, right? So there are functions that represent these integrals. You know, if I said that little f of x was equal to x, what would capital F of x be?
1/2 x squared.
Right, it'd be 1/2 x squared, right? Because the derivative of 1/2 x squared is x. Now it could also have a plus 1,000 on there, because when you take the derivative of the constant, it would go away. So we'll note, and that's why what I've written up here is capital F is any antiderivative of f, right? Because there are a bunch of different ones. 1/2 x squared plus 1, and 1/2 x squared plus 7, and 1/2 x squared minus 1,000 are all antiderivatives of x. So hopefully we're all good with the idea that a function has an antiderivative, and that antiderivative is a function. It's not just some number. So when we take an integral from a to b, all we do is we take the function that is the integral of f of x and evaluate it at b, and we take the function that is at the integral of little f of x and evaluate it at a and find the difference between them. Okay. So everybody okay with that?
Yeah.
Okay.
So there's multiple integrals for a derivative, right?
There are multiple integrals for any function.
So
Well,
how do
okay.
you choose which one?
Well, so that's what we're going to talk about in a minute. So when we have an indefinite integral, which, well, let's see, somewhere down here, I might have them in here. No, but I don't have any in here. Okay. Well, when we have an indefinite integral, what page were we on? Right here. Yeah. So when we have an indefinite integral, which is just this, an integral of 1 dx, let's say, we already know that the integral of that is x, right? So we just say x plus any constant is what we'll write, is plus c, x plus any constant. When we have a definite integral, which is when we have limits, a lower limit of a and an upper limit of b, we just choose the generic one, the easiest one, right? Because suppose we chose x plus 1,000 as our integral. Suppose we wanted to integrate this from 0 to 1. Well, if I chose just x, what do I get? The integral function is x, and so we go to the plus c now. I'd say that'd be 1, x evaluated at 1, minus 0, x evaluated at 0. Would get 1. But if I said I chose x plus 1,000, well, I'd have that evaluated at 1, which would be 1 plus 1,000, minus, and then that evaluated at 0, which would be 0 plus 1,000. And that constant, no matter what that constant would be, would always disappear. So when we have a definite integral, that constant disappears and it's insignificant. Does that make sense?
Yeah.
I'm getting a little bit ahead of ourselves, I think, but hopefully that makes sense too. So what we want to do now is step back and go back to this first part of the fundamental theorem of calculus, where we were talking about how the derivative and the integral are inverse operations of each other. And so if I'm looking for the derivative of the integral of something from a constant to x of that original function, it should come out to be that same original function, which is what we were talking about yesterday or Friday, but I think people were having some issues with it. So we're going to go back and look at these problems that we did the other day. And let's see if we can figure out why this works out. So our function is cosine of t. Can you think of a function that has the derivative that equals cosine? So what is the antiderivative of cosine?
Sine.
That should be sine, right? An antiderivative of cosine t is sine t. Right, so we're going to choose to just first work with this piece right here. I'm gonna leave my d dx, but then we're going to just evaluate this integral from negative pi to x of cosine t. So we know that an antiderivative of cosine t is sine t, and there's an infinite number of them, right? Sine t and sine t plus 1 and sine t plus 1,000 and sine t minus 1,000. But just like we saw a minute ago with the definite integral, we don't need to put the constant on because it'll just disappear when we do the subtraction. So this ends up being the sine of x, because we're going to evaluate it at the upper limit, minus the sine of negative pi, because we're going to evaluate it at the lower limit. Everybody good with that?
Yeah.
Okay, what's the derivative with respect to x of the sine of x?
Cosine.
Cosine x. And what is the negative sine of negative pi? It's a constant, right?
Yeah.
True.
Yeah.
And so when I take the derivative of a constant, it just goes away, right? Cosine x plus 0 or just cosine x. And so that's the reason why when I take the antiderivative from a constant to x and then take the derivative of it, I just end up with that same function, because the antiderivative and the derivative are inverse operations of each other. So for the upper limit, it comes out in terms of this variable, but in the lower limit, it's a constant and its derivative is 0. Does that make sense or no? Is that better than last week?
Yeah.
Yeah.
All right, cool. I thought it might be. So let's think about this one. Now we should know what the antiderivative function is of this, because we should know a function that when we take its derivative, we get this. Anybody know that function off the top of their head? You should.
Inverse tangent.
Tangent.
Yep. So we could write it out this way, and I'm going to, but we don't need to. It's inverse tangent evaluated at x minus inverse tangent evaluated at 0. And what's the derivative of inverse tangent? Well, it's 1 over 1 plus x squared. And what's the derivative of any constant? It's just 0. So we don't really need to write out this step. We know that if it's the derivative of an integral from a constant to x of some function, it's just that function in terms of x every time. Good or no?
Good.
Okay. So now what we're going to do is we're going to make it slightly more complicated. We're going to find the derivative dy dx of this function y equals the integral from 1 to x squared of cosine t. This one than the ones we were doing previously. The upper limit is no longer just a variable, right? It's not just an x up here, but it's a function up here. You guys agree?
Yeah.
Yeah.
Yeah. So since we know what the actual antiderivative function of cosine is and its sign, let's write this out. We're looking for the derivative with respect to x of, we know that the, an equal sign, of the integral of cosine, which is sine, and we need to evaluate that at our upper limit, which is x squared, and then subtract sine evaluated at 1, which we know is a constant and will disappear. So now effectively, what are we doing? We're taking the derivative of sine of x squared. And what rule do we have to use to take the derivative of sine of x squared?
Chain.
Chain rule. So this ought to become the cosine of x squared times 2x. And they love to ask questions on the AP test like this. There'll be probably one, maybe two questions where you have to use the chain rule within the fundamental theorem of calculus. And then the sine 1 is just a constant, and so its derivative is 0. Everybody good there?
Yeah.
All right, cool. So let's then take a look at this integral from 0 to x squared of e to the t squared. You probably don't know a function that is the antiderivative of e to the t squared, and that's fine. You're not going to need to. Let's just say that capital F, hold on one second. Sorry about that. All right, so let's call capital F an antiderivative of e to the t squared. And let's just sort of write this out. What does the integral from 0 to x squared of this look like? Well, it looks like capital F evaluated at x squared minus capital F evaluated at 0. Everybody agree? If capital F is an antiderivative of this?
Yeah.
Yeah.
And so then we're going to take the derivative of that with respect to x. Well, what's the derivative of capital F of a function? Well, that's the chain rule. It's the function's derivative, 2x, times the derivative of capital F. What's the derivative of capital F? Well, it's e to the t squared. So that'll be e to the x squared squared. And then minus 0. Right? So we replace the t with this function that was in the upper limit, x squared. So x squared squared. And we multiply by the derivative of that function that was in the upper limit, the x squared. Good or no?
Good.
So this becomes 2x e to the x to the 4th. You guys feel like you could do this now a little bit better than after Friday?
Yeah.
Perfect. All right. So before we go any further with those, we're going to talk about a couple of important rules of how integrals of functions or different functions can be related together, because we're going to need to use some of these rules to solve some of these fundamental theorem of calculus problems. So first off, if we have a constant inside of an integral, so a constant times a function, we can pull the constant out of the integral, just like we did with derivatives, just like we did with limits, right? So we should be able to just pull those constants out. Second, if I have an integral from a to b of f plus g, then that should be equal to the integral from a to b of f plus the integral from a to b of g. Good with that? I can separate one integral that's got two functions. Like if I had x squared plus x, I could change that into just x squared and then just plus x for each integral. Good or no?
Good.
Okay. Next one, the integral from a to a of a function is 0. Well, Hopefully that makes sense. Here's a function. Here's a. If I integrate from a to a, what's the area underneath that curve from here to here?
It's a line.
Yeah, it's a line. There's no area. I didn't go anywhere, right? It's 0. There's no area underneath the curve if there's no interval. So anytime you try to integrate from a to a, so from a constant to that same constant, it's always 0. Next thing that's important is that if I have an integral from a to b of a function, that's the same as the opposite of the integral from b to a. So you can flip your limits of integration, and we're going to show why this works in just a second. But you can flip your limits of integration and just take the opposite of the actual value. Everybody good with that or no?
Yeah.
All right, cool. And then lastly, the integral from a to b of a function plus the integral from b to c of a function ought to equal the integral from a to c. And hopefully that makes sense too, because if I have an integral from a to b, that's this area under the curve. And if I have an integral from b to c, well, that's this area under the curve. That should be equivalent to the entire area from a to c. Everybody good with that?
Yeah.
Yeah.
All right, cool. So let's use some of those rules now. So let's see if we can find the derivative of y equals the integral from x to 5 of 3t sine t dt. So first off, how is this one different than the other fundamental theorem of calculus problems that we were doing?
There's a coefficient.
What do you mean there's a coefficient? You mean the 3t that's in front of the sine t?
Yeah.
Yeah, so that's definitely out there. But that's not what I was looking for. We haven't really had it with that.
Instead of ends at x.
Yeah, okay, it starts at x instead of ends at x, right? The lower limit is x and the upper limit is 5. So let's look at this two different ways. First, let's call capital F an antiderivative of 3t sine t. Okay? And so we could write this out as the derivative with respect to x of capital F of 5 minus capital F of x. And that'd be a perfectly acceptable way to do this. What's the derivative of capital F of 5?
0.
0. And so then we should just end up with the derivative of negative capital F of x, which ought to be negative 3x sine x. Right? Everybody good there?
Yeah.
Right. Or what we could have done is we could have used our rules to say that the integral from x to 5 of 3t sine t dt is equal to the opposite of the integral from 5 to x of 3t sine t dt, which this now we know is just a constant to x, so we can just make that negative 3x sine x. So either way would have been fine. We can use the rule, or we can just write it out using the fundamental theorem of calculus part. Everybody good there or no?
Yeah, all good.
Cool. I'm not sure why that one is before this one. I don't know how we missed this one, but I want to do this one now. Let's move that around so it's in the right order. So we want to find the derivative of y equals the integral from 2x to x squared of 1 over 2 plus e to the t. So what are our thoughts with this one? This one's a little different because there's no constant, right? It's now just the lower limit of the function and the upper limit of the function. So how are we going to deal with that?
We can just do what we did before, where we just find the derivative of both of them now instead of just one.
Okay, so we'll call capital F an antiderivative of 1 over 2 plus e to the t. And this will become a derivative with respect to x of capital F of x squared minus capital F of 2x. Everybody good with that? Okay. And what's the derivative of capital F of x squared? Well, it's this function evaluated at x squared times the derivative of x squared. And same thing with the other one. That should be the function evaluated at 2x times the derivative of 2x. Or just 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So that's one option for what we could have done. Another option, everybody good with that option? Before I move on to the other way we could have done it?
Yeah.
Okay. So another thing we could have said was, well, I'm going to just draw this function. I don't know what that function looks like. I don't care what it looks like. It looks like that. We're going to pretend it looks like that. Here's 0. Here is 2x, right? This must be x, so this is 2x. And then somehow over here, a little further over at my upper limit, I'm at x squared, right? On my t and y axis here. I'm going from 0 to 2x and from 2x to x squared. So the integral we're looking for is this integral from 2x to x squared, right? No matter what x value it is. So if x was, 5, well, this would be from 10 to 25. If x was 1, then this would be an integral from 2 to 1. And our thing looks a little weird, but that's okay. It doesn't really matter. The integral will sort out the negative signs for us. So we could have said this could equal the integral from 0 to x squared of 1 over 2 plus e to the t dt minus the integral from 0 to 2x over 1 over 2 plus e to the t dt. And so it would be 0 to x squared minus 0 to 2x, and that would give us this section between of 2x to x squared. Does everybody see that?
Yeah.
Yep. And so then when we were to take the derivative of all of this, it would just be this function evaluated at x squared times the derivative of x squared minus this function evaluated at 2x times the derivative of 2x. Constants would go away and you'd get this exact same thing. So either way would be good. Any issues, problems, questions with that? Everybody okay with that?
Good.
Good.
Okay. Cool. All right, we're going to do one more question, which is a little bit different now, and then we're gonna actually stop for today. I'm going to give you guys time to work on your homework and all that for the rest of the time, so you can ask questions on it because it's a little more than it's 2 assignments tonight instead of 1. So, and I'm sure you'd like time to study for your quiz tonight rather than having homework to do. So, if we've got 2 functions f and g that are continuous, and we know some of the values of some of the integrals, like the integral from 1 to 2 of f, or from 1 to 5 of f, or 1 to 5 of g, we should be able to find some other related integrals. So first off, from the information given to us, what's the integral from 2 to 2 of g of x?
0.
0.
0. We should know that always, right? The integral from a to a of any function is always 0. What about the integral from 5 to 1 of g of x? Using our rules, that should be equal to the opposite.
-8.
Right, the opposite of the integral from 1 to 5. I'm just going to write it out just for the sake of making sure we all know the rules. That should be the opposite of 8. Everybody good there?
Yeah.
Yeah.
Okay. What about the integral from 1 to 2 of 3 times f of x?
-12.
So that ought to be 3 times the integral from 1 to 2 of f of x, and the integral from 1 to 2 of f was -4, so that's 3 times -4. Sorry, I got it. Somebody asked me in the chat about why that's -8. So our rule from way up here was that we can flip the limits of integration. And if we flip the limits of integration, you put a negative sign out in front of the integral. So for here, we had an integral from 5 to 1 of g. So if we flipped it to make it the opposite of the integral from 1 to 5 of g, it should be the opposite of 8. Everybody good with that?
Yeah.
Okay. Then everybody good with the next one too? Pulling the constant of 3 out and then just doing the integral from 1 to 2 of f times the 3?
Yes.
Okay. What about the integral from 2 to 5 of f?
You would add the 1 to 2 and the, or wait, no, you would subtract the 5 to 1 from the 1 to 2, right?
You mean the 1 to 5?
Yeah.
Not the 5 to 1. We don't have a 5. We have a 5 to 1, but that's not what we want to subtract. We got to do the integral from 1 to 5 of f of x minus the integral from 1 to 2 of f of x. And that ought to give us only the part between 2 and 5. So from 1 to 5 is 6, and from 1 to 2 is -4. So that ought to give us 10. Everybody good there?
Which rule did you use there?
So that one was the last rule down here, that a to b plus b to c is a to c. And so we just subtracted one of them from one side, right? Because 1 to 2 plus 2 to 5 ought to equal 1 to 5. So 2 to 5 ought to be 1 to 5 minus 1 to 2. Good?
Okay, thank you.
Yep. All right, and then so for this last one down here, this ought to equal the integral from 1 to 5 of f minus the integral from 1 to 5 of g, and 1 to 5 of f is 6, and 1 to 5 of g is 8. So it ought to be -2. Everybody good with that? Any questions on that?